Before we get into electron affinity, let's really quickly review ionization energy. And let's start with a neutral lithium atom with an electron configuration of 1s2, 2s1. A lithium atom has 3 protons in the nucleus, so a positive 3 charge, 2 electrons in the 1s orbital, so here are the 2 electrons in the 1s orbital, or our core electrons, and 1 electron in a 2s orbital. This is our outermost electron, our valence electron. The valence electron is shielded from the full positive 3 charge of the nucleus by the presence of the core electrons. So like charges repel, and these core electrons repel this outer electron and shield it from the full positive 3 charge. But there still is an attractive force between the positively charged nucleus and this outermost electron. So opposite charges attract, and our outermost electron still feels a pull from the nucleus. Therefore, since the outer electron is attracted to the nucleus, it takes energy to completely pull away this valence electron from the neutral atom. So if we pull away that outermost electron, we lose our valence electron and we're left with a lithium ion with a positive charge. Positive 1 charge because we still have 3 protons, but only 2 electrons now, so overall a +1 charge. Since this ionization takes energy to rip away the electron, the ionization energy is positive and it's measured in kilojoules per mole. Let's compare that with electron affinity. So in electron affinity, let's say we're starting with our neutral lithium atom again, but this time, instead of taking an electron away, we are adding an electron. So we would add an electron to the 2s orbital. So we started off with 3 electrons in the neutral lithium atom, and we're adding 1 more. So the electron configuration for the lithium ion would be 1s2, 2s2. So still 3 positive charges in the nucleus, 2 electrons in the 1s orbital, but now we've added an electron, so we have 4 electrons total, 2 in the 2s orbital. So let me highlight the electron that we added in magenta. So this is the electron that we added to a neutral lithium atom. And this electron, we know, is shielded from the full positive 3 charge of the nucleus by our 2 core electrons in here, right? So like charges repel. It's also going to be repelled a little bit by this electron that's also in the 2s orbital. So this electron is going to repel this one as well. But there is an attractive force between our positively charged nucleus and our negative charge on the electron. So this electron that we added still feels an attractive force that's pulling on it from the nucleus. And so if you add this 4th electron, energy is given off. And since energy is given off, this is going to have a negative value for the electron affinity. For adding an electron to a neutral lithium atom, it turns out to be -60 kilojoules per mole. So energy is released when an electron is added. And that is because the electron that we added is still able to be attracted to the charged nucleus. So if the nucleus has an attraction for the added electron, you're going to get a negative value for the electron affinity, or that's one way to measure electron affinity. Note that the lithium anion is larger than the neutral lithium atom. It's just hard to represent it here with those diagrams. So as long as the added electron feels an attractive force from the nucleus, energy is given off. Let's look at one more comparison between ionization energy and electron affinity. In ionization energy, since the outer electron here is attracted to the nucleus, we have to work hard to pull that electron away. It takes energy for us to rip away that electron. And since it takes us energy, we have to do work, and the energy is positive in terms of ionization energy. But for electron affinity, since the electron that we're adding is attracted to the positive charge of the nucleus, we don't have to force this. We don't have to do any work. Energy is given off in this process, and that's why it's a negative value for the electron affinity. Electron affinities don't have to be negative. For some atoms, there's actually no attraction for an extra electron. Let's take neon, for example. Neon has an electron configuration of 1s2, 2s2, and 2p6. So there's a total of 2 plus 2 plus 6, or 10 electrons, and a positive 10 charge in the nucleus for a neutral neon atom. So let's say this is our nucleus here with a positive 10 charge, 10 protons, and then we have our 10 electrons here surrounding our nucleus. So this is our neutral neon atom. If we try to add an electron, so here let's add an electron, so we still have our 10 protons in the nucleus, we still have our 10 electrons, which would now be our core electrons. To add a new electron, this would be the neon anion here. So 1s2, 2s2, 2p6, we filled the second energy level. To add an electron, we must go to a new energy level. So it would be the third energy level, it would be an s orbital, and there'd be one electron in that orbital. So here is, let's say this is the electron that we just added. So we have to try to add an electron to our neon atom. But if you think about the effective nuclear charge that this electron in magenta feels, right? So the effective nuclear charge, that's equal to the atomic number or the number of protons, and from that you subtract the number of shielding electrons. Since we have 10 protons in the nucleus, this would be 10, and our shielding electrons would be 10 as well. So those 10 electrons shield this added electron from the full positive 10 charge of the nucleus. And for a quick calculation, this tells us that the effective nuclear charge is 0. And this is, simplifying things a little bit, but you can think about this outer electron that we tried to add of not having any attraction for the nucleus. These 10 electrons shield it completely from the positive 10 charge. And since there's no attraction for this electron, energy is not given off in this process. Actually, it would take energy to force an electron onto neon. So if we wrote something out here, if we said, all right, I'm trying to add an electron to neon to turn it into an anion. Instead of giving off energy, this process would take energy. So we would have to try to force this to occur. So it takes energy to force an electron on a neutral atom of neon. And we say that neon has no affinity for an electron. So it's unreactive, it's a noble gas, and this is one way to explain why noble gases are unreactive. This anion that we intended isn't going to stay around for long, so it takes energy to force this onto our neutral neon atom. So you could say that the electron affinity is positive here, it takes energy, but usually you don't see positive values for electron affinity for this sort of situation. At least most textbooks I've looked at would just say the electron affinity of neon is 0, since I believe it is hard to measure the actual value of this. Here we have the elements in the second period on the periodic table, and let's look at their electron affinities. We've already seen that adding an electron to a neutral atom of lithium gives off 60 kilojoules per mole. Next we have beryllium with a 0 value for the electron affinity. That means it actually takes energy, so this number is actually positive, and it takes energy to add an electron to a neutral atom of beryllium. So if we think about going from a neutral atom of beryllium to form the beryllium anion, when we look at electron configurations, neutral atom of beryllium is 1s2, 2s2, and so to form the negatively charged beryllium anion, it would be 1s2, 2s2, and to add the extra electron, it must go into a 2p orbital, which is of higher energy. And so this is actually the same thing, or very similar to neon, which we just discussed. For neon, the electron configuration was 1s2, 2s2, 2p6, and to add an extra electron, we had to go to the third energy level. We had to open up a new shell, and the electron that we added was effectively screened from the full nuclear charge by these other electrons. And a similar thing happens here for the beryllium anion. To add this extra electron, we have to open up a higher energy p orbital. This electron is on average further away from the nucleus and is effectively shielded from the full positive charge of the nucleus, and therefore there's no affinity for this added electron. So there's no affinity for this electron, so it takes energy to form the beryllium anion, and that's why we see this 0 value here for beryllium. Beryllium has no value for electron affinity, or it's actually a very positive value, and we just say it has a 0 value. Next, let's look at boron here. So this gives off negative 27 kilojoules per mole. And we can see a little bit of a trend here as we go from boron to carbon to oxygen to fluorine. So as we go across the period on the periodic table, more energy is given off, and therefore fluorine has the most affinity for an electron. So as we go across a period, we get an increase in the electron affinity. So the negative sign just means that energy is given off, so we're really just looking at the magnitude. More energy is given off when you add an electron to a neutral atom of fluorine than if you add an electron to a neutral atom of oxygen. And we can explain this general trend in terms of effective nuclear charge. As we go across our period, we also have an increase in the effective nuclear charge. And if the added electron is feeling more of a pull from the nucleus, which is what we mean here by increased effective nuclear charge, more energy will be given off when we add that electron. So this idea explains the general trend we see for electron affinity. As you go across a period, we get an increase in the electron affinity. We've already talked about beryllium as an exception, neon as an exception, but what about nitrogen in here? We can see that nitrogen doesn't really have an affinity for an electron, and you'll see many different values for this one depending on which textbook you're looking in. But if we look at some electron configurations really quickly, we can try to explain this. So for nitrogen, the electron configuration is 1s2, 2s2, and then 2p3. So if we draw out our orbitals, let's just say this is the 2s orbital, and then these are the three 2p orbitals. So we'll just do these electrons here. 2 electrons in the 2s orbital, and then we have 3 electrons in the p orbitals. So let's draw those in there. If we try to add an electron to a neutral nitrogen atom, we're adding an electron to one of these orbitals which already has an electron in it. So adding an electron to one of these orbitals, right, the added electron would be repelled by the electron that was in there to start with. And this is the reason that you usually see in textbooks for the fact that this does not follow the trend. Nitrogen doesn't have an affinity for one added electron. So after going through all of that, it's obvious that electron affinity is a little more complicated than ionization energy. And ionization energy we had a pretty clear trend, and it was a little easier to explain why. For electron affinity, going across a period on the periodic table, we see a little bit of a trend, but there are many exceptions to this, and perhaps our explanations are a little bit too simplistic to explain actually what's going on. But across a period, you do see a little bit of a trend. Going down a group is much harder. You see more inconsistencies, and it's not really even worth going over a general trend for that.